Okay, you're on. So wait, I'm hearing you're quitting high school, dropping out of high school. No, don't do it. To go to college full time.
Yes. Maybe get like a part-time job. That'd be nice.
Yes, because I need to not work so much. You can support me. Anyways, clean coal. Is there such thing as clean coal?
Well, of course not. Right? It's like, so like the only thing coal really emits when you burn it is CO2. CO2, right? Which of course is the product of a fire. If you burn coal, right? Coal, by the way, here's a very bad chunk of coal, but
so it's worse than actually oil, right?
Yeah. If you want to produce, say, a gigawatt of energy using oil, then a gigawatt of energy versus coal, the coal will produce 4 times the amount of CO2.
Oh, great. So let's dig that stuff up and run our electricity on it.
Obviously, when you're burning the coal, which is, by the way, pure carbon, obviously the bonding of the carbon goes into, it can either go into CO2 or just, which is carbon dioxide. So it can either go CO2 or just CO, which is carbon monoxide, which is harder to get out of the atmosphere, but most of the time it comes out in CO2. Anyways, point being, you cannot have clean burning coal because coal is carbon.
Right.
So by definition, burning coal means you have to produce one of these. There's no way that you can burn this and not produce this but get energy out of this.
Okay.
It would violate laws of conservation of energy, which just wouldn't make sense.
So anyway, so I saw this thing today where they said that, somebody was saying, it was actually a pretty good video, saying that, as the ice melts and it goes down, the thousands and thousands, possibly millions of years, it's actually releasing, or could release, some of the old diseases
that
we have eliminated, and that could be dangerous to us.
So I will say that there is a little bit of validity to that. You can dig up, you got layers here, and you got, here's layer 1 and then layer 2, and you'll notice that they get kind of thinner and thinner as you go down because it's more and more compacted. But so you'll find like little dots in there, and you can actually study past microbes. It's not too common, but you can do it. You can study past diseases like that. But the thing is, so like really, anything like bacteria from the past that was deadly to us, that's not going to work out because bacteria are filled with water, and of course, bacteria filled with water. The water in the cell is, it's right here. But as it freezes, it actually expands and it forms shards and crystals, so it'll punch holes through the cell wall. So that's fine. Technically it could be revived, but once you unfreeze it, right, then all these holes are there and you've got all this fluid leaking out and this thing dies. Now there is the chance that if this freezes fast enough, the ice could freeze in more of a crystalline, like a nice smooth structure, which, that could potentially mean that it could come back, but that's so unlikely. What you really need to worry about is viruses, because viruses don't use water in their shells, to my knowledge. I could be wrong about that, but those things are way more versatile because they're technically not alive. They don't have as much complicated machinery as bacteria. They're just kind of like, this sort of structure. Some of them are kind of cell-like. I think the HIV virus looks kind of like that. It's got it's circular, but it's got pieces of it sticking out, I think.
Yeah, I mean, they mentioned Ebola and Zika virus, I think, in the video.
Yeah, maybe.
Maybe
I could see that, yeah.
Brought back or something.
I could see that.
All right, so here's the other thing. My new discovery. The photon. So the difference in, so we could see a photon that is was created 14 billion years ago or 13 billion years ago, and we're looking at it. But for the photon, it's only been an instant. Yeah. Not even a second. It was just created then and there.
So there's two ways to think about that, which is, so relativity, I'll explain that a little bit for people who don't understand it. Number one, this is actually the equation for how you calculate time dilation. I'll write it bigger. T equals, this is this little dash up here means prime.
This is Einstein's.
T prime. Yeah, T prime equals time. This is the time of the person observing the person in motion. Is times the square root of 1 minus v squared c squared. Now I'm going to put little parentheses here, but you technically don't have to because of order of operations. Anyways, so the thing you'll notice about this equation, right, is so what you'll do is you take the time, let's say 1 second, you run it and all that. But the thing you'll notice is over here, if the velocity equals the speed of light, well, let's assume this is the speed of light, so we get equals t square root 1 minus c squared divided by c squared. Well, that's 1, so you cross that out, equals t square root 1 minus 1 equals 0, t square root of 0, which is 0, so you just get 0. So when you hit the speed of light, time, t prime, becomes 0. There is no amount of time that will elapse over any amount of time relative to the stationary observer. So what this means is if I hit the speed of light, time doesn't elapse for me.
At all.
At all. And so I'll go into a little bit of conceptualism here. The reason this is a better way to think about it rather than mathematically is so I always like Brian Greene's explanation. So Brian Greene, all credit to you.
Can you do it in 2-3 minutes?
Yeah, real simple. Let's imagine I have a race car, and the race car is going like this. This is a 10-mile track. The race car travels at 100 miles per hour. It should only take me about 6 minutes to get across the track if I'm going in this direction. But as the day goes on, maybe the sun gets in my eyes, so I start to go like that. And then maybe a little more like that, and maybe a little more like that. So now it takes more and more time. Maybe it's starting to take 6 minutes 30, now 7 minutes, now 7 minutes 30. And it's because I'm sharing my space, or my speed, through 2 dimensions, right? So it means that I'm sharing my speed through 2 dimensions. So if we think of time like another dimension, right? I'm moving through this direction of space. This is time. But if I want to walk, if I want to increase my speed through space, well, now I've got to divert some of that. So I'm still moving through time, but now some of my speed is going into space.
Right.
And eventually, if I go fast enough, I'm just going through space and not time.
But it will still be the same amount of time.
Kind of. And so...
All right, did I mess that up?
So... Well, I don't exactly know what you mean by the same amount of time.
Well, from the photon's perspective,
well, okay, so
same time elapsed doesn't matter the distance.
It doesn't really feel. The other way to think about it is so in one of Einstein's points that he made is that as you travel through space, space contracts. So if I'm standing here and I have wall A and wall B, right? If I'm here and I measure, this is 1 meter apart, right? And then I travel in this direction at, I don't know, let's say 50 meters a second or something. Well, I'm going to start to measure the distances just a little bit closer. Maybe it's 0.995 meters close. And then, as I speed up, it gets closer and closer. So likewise, when you hit the speed of light, wall A and B will be literally on top of each other. Space becomes 2-dimensional when you hit the speed of light. So it's like the photon, let's say it's being emitted from 14 billion light years away, right? And then, it's coming over here. Well, from our perspective, it's traveling all this distance. But from its perspective, these 2 points are the same point.
Wow. All right. That was it.
Yep.
10-minute video.